since we've been talking about roots, there is another type of root that gets that isn't always something that most people realize, and that's dealing with complex numbers and imaginary numbers. Now, remember that an imaginary number, the I, is the square root of -1. Okay, so the tricky thing with this is when you have a negative square root, it's going to have the I, but the I gets pulled out from underneath the square root. So for instance, if we were to have the square root of -5, that negative here gets pulled out as an imaginary number. So this actually goes to I square root 5. Now, there are times when you might have a more challenging square root, such as the square root of, let's go -20. Well, the square root of a regular 20 can actually be broken down, in which you need to do the same thing here. So I'm going to break it down using my simplifying radicals properties. The perfect square that can be pulled out is a 4. I'm going to make it negative because that's going to hold my imaginary number. 4 times 5 gives me that 20. That -4 square root 4 goes down to 2i. So this is actually 2i square root 5. So notice here what's different. The thing that's different is you started as a negative number, but then it turned into a positive number, and that's because we used the imaginary number. Okay, so how else can we use imaginary numbers or complex numbers? You might also have to multiply them. So if I were to have 3 plus 2i times 5 minus 3i, I'm going to have to distribute these in order to get it reduced down. What makes this a complex number? What makes this a complex number is you have a 3 here without an I, so this is real, and then the 2i is imaginary. Hence, the whole thing together is a complex number. Okay, so going back to our original goal here that we're supposed to multiply, I'm sorry, I just wanted to break that down for you. We're just actually distributing, so it's nothing too challenging. So I have 3 times 5 gives me 15. 3 times -3i gives me -9i. Now I'm going to go ahead and distribute that 2i. And I get positive 10i and then minus 6i squared. So let's actually talk about the 6i squared. So if I equals the square root of -1, if I were to square both sides, well, what happens to a square root when it's squared? It cancels out. So I squared is realistically -1. So that's actually going to alter my answer here. So I've got 15 plus 1i minus 6 times -1. Well, -6 times -1 is a positive 6, so I can actually add the 15 and the positive 6. So realistically, my answer to this is 21 plus 1i. Now, there are times that you will need to multiply by what's called a complex conjugate. A complex conjugate. So let's say that I have 3 plus 2i. The complex conjugate of this is 3 minus 2i. So the only thing that changes is the sign in front of the 2i. So don't get confused if this were 2i plus 3. This actually does not go to 2i minus 3. It goes to -2i plus 3. So just something to note. It's the sign in front of the in front of the imaginary number. You will want to multiply by the complex conjugate when you have a fraction. You cannot have an imaginary number in a denominator. So this is no different than if you were to have a square root in a number. So if I were to have 2 plus 3i divided by 4 minus I need to multiply by the complex conjugate. The complex conjugate here is going to be 4 plus I. And just like the last problem, I'm going to have to do some distribution and simplification. So I'm going to work with just the top here. I've got 8 plus 2i plus 12i plus 3i squared. On the bottom, I'm going to have 16 plus 4i minus 4i minus I squared. So what makes this eliminate your I in the denominator is that middle term there, that 4i minus 4i. That cancels it out. And so that's why we multiply by the complex conjugate. So on top here, realistically, I've got 8 minus 3 to give me 5 plus 14i. On the bottom, like I said, these cancel out. And then you have that negative 1. So that's actually going to go down to 17. All right. So some of you might be saying, okay, this is great, Mrs. Fish, but when are we going to use this? So going back to, we were dealing with roots before, right? So if I'm still looking for a root, which I might be, you might have to simplify and use imaginary numbers when you're dealing with, say, specifically quadratics. If I were to have x squared plus 16, and I want to find the roots, I know I have to set this equal to 0. Well, I'm going to have to solve for x to find the roots. So algebraically here, I'm going to move that 16 over, so x squared equals a negative 16. Well, to get rid of a square, I have to take the square root. And that's where my complex conjugate or my imaginary numbers come into play. My root is actually an imaginary number. X is going to equal plus or minus 4i. So that's my root. So if I wanted to list this as factors, this would be x minus 4i times x plus 4i. So we've dealt with real roots and real factors so far, but there are times when you will have imaginary roots. And this is going back to when we were talking about the degree and all of that information. It's all tied together now that we've got our real and imaginary roots.